In Chapter 5, we're going to have a brief discussion about thermodynamics as it relates to chemistry, and that leads us to the topic of thermochemistry. So this section will be kind of a fundamental introduction to some of the key concepts of thermodynamics that we want to consider. The more detailed stuff with regard to thermochemistry is primarily saved for the second semester class. So, of course, if we're talking about thermodynamics as it relates to chemistry, then one of the first things we want to talk about would be energy. So when we think about energy, we need to consider that it essentially can exist in two forms. And so when we talk about energy, it's either the ability to do work or to transfer heat. Energy used to cause an object that has mass to move is called work. So if I lift a weight or slide something across a surface or even blow up a balloon, that would be mechanical work. Energy used to cause the temperature of an object to rise is called heat. So one of the ideas we want to think about pretty early on here is that energy is interchangeable between energy used for work or energy used as heat. Another distinction we want to make when we talk about energy is potential energy and kinetic energy. So generally when we talk about potential energy, it's the energy an object possesses by virtue of its position. So typically when we talk about potential energy, we'd be thinking about a stationary object at the top of a hill has potential energy because of its height at the top of the hill. We can also think about potential energy in terms of the chemical composition of a substance. We won't really get too much into that in this section, but that's another time where we can think about potential energy. When we think about potential energy, we also want to talk about kinetic energy, and that's energy an object possesses by virtue of its motion. So an object that's in motion, that would have kinetic energy. And the m in this equation is the mass in kilograms, and the v in this equation, that's the velocity, so the speed in meters per second. So to calculate the kinetic energy of an object, it would be 1/2 times the mass in kilograms times the velocity in meters per second. So you can imagine we would have kilograms and then meters per second quantity squared. So you get a unique unit of kilogram meter squared per second squared, but that ends up being the SI unit for energy. So now we're comparing the potential energy of the stationary bicyclist where she's at the top of the hill to now she's in motion coming down that hill. So now initially stationary, it's all potential energy, but now as she moves, potential energy is getting converted into kinetic energy. So like I said, this leads us to the SI unit of energy called the joule, and it's 1 kilogram meter squared per second squared. So I think the easiest way to see where that unit is coming from is by looking at the kinetic energy equation where it's mass times velocity squared. So this is a compound unit that also contains squared and cubed units. A lot of times when we talk about energy, we'll talk about the calorie instead, and the calorie is a non-SI unit, and 1 calorie equals 4.184 joules. So the calorie is defined in a unique way, and 1 calorie is the energy needed to heat 1 gram of water by 1 Celsius degree. So the calorie is defined in terms of energy and heat flow, but remember the unit is interchangeable. So whether I'm talking about kinetic energy, potential energy, energy transferred as heat flow, energy used for work, all of these are going to have the same unit of energy in the SI system. That would be the joule. But that's how a calorie, which may be a unit you're more familiar with, that's how that is defined. And if you're comparing this calorie to food calories, well, food calories are actually kilocalories, so thousands of calories, but usually you just see it written with an uppercase C to indicate that it's thousands of calories, kilocalories, instead of just calorie. So a lot of what we're interested in thermochemistry is heat flow. And when we think about heat flow, the direction of that heat flow is important. So we want to define the system and we want to define the surroundings. The system is pretty simply the stuff that we're interested in studying, so the molecules we want to look at, and the surroundings are just everything else. So in this case, the container, that piston that is movable, all the other stuff. So the reason that we want to clearly define system and surroundings, at least with regard to heat flow, is we want to be able to talk about whether heat is flowing from the system to the surroundings or heat is flowing from the surroundings to the system. But more generally, the system surroundings definition is important because we can define the part that we're interested in versus the part that we're not as concerned with. All right, so if we want to talk about work, the classical physics equation to describe work is work equals force times distance. So if you imagine that we have a surface and we have a mass on that surface and we want to slide this mass across the surface, there's going to be some sort of force, a frictional force of the surface, let's call it, that's counteracting our motion, and then we're going to move this object over some distance against this counter force. So the way we figure out the energy required to slide a mass across this flat surface with some frictional force is it's the force times the distance that the object is sliding against that force. So force times distance will give us a value in energy as well. Where else can we think about this? Turning a wheel inside of water, blowing up a balloon, lifting an object, anything like that would fit into work. So we will see an example of how work can exist in a chemical system, but it's relatively rare that we get concerned with that. Well, heat is a lot easier to think about, right? When we talk about energy being transferred as heat, it's just energy being used to heat something up. And this is a very obvious statement, but something to hopefully be aware of, that when we think about heat flow, we can imagine putting two objects that are at different temperatures in contact with each other. And no matter what, right, heat is going to flow from the warmer object to the cooler object. So we can revisit our kinetic and potential energy with our cyclist again, and just the general idea that energy can be converted from one type to another. That's very important to keep in mind. And so I think I said this earlier, the bicyclist at the top of the hill has potential energy, and then as she starts to coast down the hill, potential energy is converted to kinetic energy. When we get to the bottom of the hill, technically zero sea level, all of the potential energy she had at the top is now kinetic energy. But not only do we observe this conversion of energy, we're also going to observe a conservation of energy, meaning all that initial potential energy is now shown to be the kinetic energy at the bottom of the hill. So we'll start here with the first law of thermodynamics, and there are a lot of different ways to say it. To start with, I'll say it in words in two different sentences, and then we'll see how it is reflected in a mathematical equation as well. So the easiest way to say the first law of thermodynamics is simply to say energy is neither created nor destroyed. And that's a thorough description of what the first law of thermodynamics tells us, but what it's really telling us is a couple things. One, the total energy of the universe is a constant value, and two, if the system loses energy, it must be gained by the surroundings. If the surroundings lose energy, it must be gained by the system. So we can kind of do this broad bookkeeping of the energy of the universe, basically saying if we know what change the system is undergoing energetically, we understand the surroundings is undergoing the opposite change in our particular view. And so that's something important to be able to do, right? Because to calculate what's going on in the surroundings is not particularly easy to do, but understanding from the perspective of our particular system that the system change and surrounding changes are opposites, that's something good to be aware of. So as we think about the first law of thermodynamics, something that we want to think about is internal energy. And the internal energy of a system is the sum of all the kinetic and potential energies of all the components of the system. And it's just symbolized by capital E. So now what we can see is two pictures describing what's going on with regard to the internal energy of the system. So we've got our initial state with some initial value of internal energy. Then we've got a final state with some other value of the final internal energy. So in this case, we can see that the final value is lower than the initial value. So the internal energy of the system is decreasing. It's negative, which means, so delta E is negative, which means energy is being lost to the surroundings. So if the final state has a lower internal energy than the initial state, then that means the system, that's what we're looking at, is losing energy to the surroundings. We could also have it the other way with an initial state and a final state. Here are the respective energies. And now we're seeing a final energy higher than an initial energy. So that means the system is gaining energy. And we can't just gain energy, it needs to be gained from somewhere. So if the system is losing energy, it's losing it to the surroundings gain that energy, and if a system is gaining energy, it's receiving that energy from the surroundings. In the brief look at thermochemistry we're going to get to, we'll think about this idea a little bit, but it'll come up more in more complicated situations, which, like I said, are primarily things that we'll talk about in the second semester class. So what we observed there is we didn't actually ever calculate a value for internal energy. We calculated the change in the internal energy. So every time you see this delta symbol, remember that always means change in, and it always means final minus initial. So anytime it's delta, it's always the final value minus the initial value. So if the value goes down during the course of the process, delta E is negative. If the value goes up during the course of the process, delta E is positive. So notice, effectively, we're not really obligated to get an actual value for the internal energy itself. We can just observe the change in the internal energy during the course of a process. And that's important, right? Because actually figuring out a value for the internal energy might be challenging, whereas figuring out how it's changing, that's a bit more straightforward to do, right? To actually evaluate the internal energy of a system, I would need to consider every particle and do its kinetic and potential energy values in each case, which that could be very challenging, especially when we get to a relatively large system. But instead, we can focus on the way in which this value is changing and look at delta E, the internal energy change. So let's look at a reaction that I think we considered a couple times before. In this case, we're looking at the decomposition of water into its component elements, right? 2 H2O turning into 2 hydrogen molecules and 1 oxygen molecule. So this process costs energy, right? I need to supply energy to the water to break it apart into its component parts. And so when I do that, we would say the internal energy change is positive. I needed to increase the amount of internal energy to make this process go, right? There needed to be an input of energy to break those water molecules apart. If we have a process that involves an increase in internal energy, and here we'd say the system absorbed energy from the surroundings in order to make it happen, we describe that process as endergonic. So we're going to have exergonic and endergonic. Endo meaning inward, exo meaning outward, like exoskeleton. So here we're looking at the reaction in which we break water apart into its component parts. That costs us energy, so we say the system had to absorb that energy from the surroundings. Since the final internal energy is higher than the initial, we'll call this process an endergonic process. Energy is flowing inward from the surroundings to the system. Well, instead, we could flip this equation around, right? So rather than looking at it this way, we could say, what if we want to convert hydrogen and oxygen into water? Well, it turns out that's an energetically favored process. Hydrogen and oxygen combining to water, that's going to be a case where the internal energy change is less than 0, because the final state is lower in energy than the initial state. That should make sense, right? If I know what's going on in one direction, then I should be able to rationalize that the opposite is going on in the other direction. So now we'd say that the system released energy to the surroundings. So it's going outward. So we'd say that this is an exergonic process. Remember, exo like exoskeleton. Energy is flowing outward from system to surroundings. So since this internal energy change is negative, we describe the process overall as being exergonic. So what are we really thinking about with changes in internal energy, right? I was saying we're not really evaluating the actual value for the internal energy. We're evaluating how it changes. Well, there's only 2 ways the internal energy value can change, either through heat flow between system and surroundings, or through work being done either by the system or on the system. Most of the time in chemistry, we're primarily just concerned about heat flow, so that'll become our main focus later on, but it is still possible that some internal energy change is related to some sort of mechanical work taking place in our system. All right, so here it's showing that for heat, we use the symbol Q. I actually don't know the official reason for that. I guess after all this time I could look it up. And mechanical work is symbolized simply by W, so that's how we get our equation, delta E equals Q plus W. So we saw 2 different ways to say in words what's going on with the first law of thermodynamics. Mathematically, this is the simplest way to say it, that if there is internal energy change in the system, it's either through heat flow or mechanical work. So remember, one way to say it is energy is neither created nor destroyed. Another way to say the same thing is the total energy of the universe is constant, but now we're saying if there is an internal energy change, it will either be due to heat flow or mechanical work. So then what does that all really mean? Well, we've kind of dealt with the first part of this already, right? If delta E is greater than 0, then energy is flowing into the system. If delta E is less than 0, flowing out of the system. So endergonic for flowing into, exergonic for flowing out of. Then what about heat flow? Well, if Q is positive, that means heat is flowing into the system. Makes sense. If Q is negative, heat is flowing out of the system. So that's kind of following the same logic that we've seen before. Mechanical work, which again, I haven't really given you a good example for how it would exist in a chemical system, but mechanical work, it's a bit trickier and we will get to it, but if the sign of work is positive, we'd say work is being done on the system by the surroundings. If work has a negative sign, then work is being done by the system on the surroundings. So whichever one is performing the work, that's what's losing energy. If the surroundings are doing work on the system, that's energy transferring into the system. If the system is doing work on the surroundings, then the system is losing energy through work. So then lastly here in this video, we'll get to some vocabulary that maybe looks a little bit more familiar. I think you talk endergonic and exergonic in biology class as well, but probably if you remember some of this terminology from high school chemistry or a previous chemistry class, you probably remember endothermic, exothermic more than endergonic, exergonic. So now we're exclusively talking about heat. And here we're saying if heat is absorbed by the system from the surroundings, we describe the process as endothermic. So heat flowing into the system from the surroundings, so inward, so endothermic. And you can see in the picture here, it's showing heat flow from surroundings into the system, so that's endothermic. And then on the other side, right, if this is endothermic, then now we're showing heat being released by the system to the surroundings. That's when it's going to be exothermic. So flowing outward from system to surroundings, again, exo like exoskeleton, that's going to be exothermic. And flowing into the system from the surroundings, that's going to be endothermic. Okay, so that was a quick run in some of the fundamental vocabulary we want to talk about here in this chapter. I think in the next video I'll introduce a couple more terms, but we'll start to shift toward doing some calculations fairly quickly in this section once we get there. But these are some of the key terms, which again you may be familiar with from a previous course, but just want to make sure we're all on the same page with this vocabulary. So I'll go ahead and stop this video here, and then we'll pick up, it looks like, on slide 20 in the next video.